presentation is entitled MedAgentSim, Self-Evolving Multi-Agent Simulations for Realistic Clinical Interactions. This is going to be presented by Mohammad Almansoori from the Mohammed bin Zayed University of Artificial Intelligence from the United Arab Emirates.
Thank you so much. Good evening, everyone. My name is Mohammad Almansoori from Mohammed bin Zayed University. And I'll be presenting our paper today, MedAgentSim for Self-Evolving Multi-Agent Simulations for Realistic Clinical Interactions. So to start, let me show you how the simulation works. We have two agents here, one named Doc, which is the doctor, and Pat, patient. Each of these agents, they're powered by a large language model, so basically every decision they make, their movement, all of that is powered by that same LLM. So yeah, the process begins when the patient develops symptoms and enters the hospital. They are looking for the nearest doctor. Once the patient finds a doctor, the consultation starts. At this point, the doctor knows nothing about the patient's information, nothing is provided upfront, nothing about the condition. So through a back and forth dialogue, the doctor asks questions to gather information. So for example, symptoms, history, etc. Based on that relevant history, the doctor can also request medical imaging, medical tests, CT scans, X-rays, etc. So there's a medical agent that provides that information and that result to the doctor. But if the doctor agent does not request that information, he is not provided with it. After he receives that information, he discusses with a group of medical agents as well. They, using ensembling, they discuss together and they come together to come up with a final diagnosis, which they provide the agent, and at that point, the simulation ends. But for now, let's just take a step back and give a quick background. So, as you should all know, large language models, or LLMs, like ChatGPT, they're trained on massive collections of text. They've shown great ability in reasoning and language generation in general. So this has enabled strong performance on tasks like question answering, summarization, and even dialogue. So an agent is just an autonomous system that's powered by an LLM that can perceive its environment and act on it. So in systems like where we have several agents, multi-agent systems, they usually collaborate or even compete at times. For example, like this simulation where we have doctors, patient, and measurement tools. This opens up a much richer interaction dynamic. So usually in healthcare AI, most evaluation metrics so far, they've been using static benchmarks. Well-known examples include MedQA, PubMedQA, and MultiMedQA. These data sets from, the problems they present, they're usually multiple choice. They're multiple choice questions. The model is given all the patient information up front, and the model is asked to basically just pick the correct answer from a list of choices, which kind of brings me to the current challenge. So most existing evaluation benchmarks, like I just mentioned, prompt-based or MedQA, they provide the large language model with all the patient information at once. So symptoms, lab values, imaging results, everything is already neatly packaged. The model's task is then to simply just select the correct answer from a set of multiple choice options. This setup, it makes the evaluation straightforward, but it is rather oversimplified and doesn't really reflect how diagnosis actually happens in practice. So in the real world, as you should know, patients, they rarely present with perfectly structured information. They may describe their symptoms vaguely, incompletely, or even at times incorrectly. So physicians, they need to guide that conversation, and they need to ask clarifying questions, decide when to order tests or imaging before they can form a diagnosis. So the gap here is clear. Current benchmarks, they measure pattern recognition, but they don't really capture the interactive, uncertain, multimodal, really, reasoning that defines clinical practice. So let me briefly position our work in the context of existing efforts. Traditional medical question answering benchmarks like MedQA, PubMedQA, etc., they've been important for measuring baseline knowledge, but they don't really capture the narrow slice. They only capture a narrow slice of the diagnostic reasoning. So more recently, simulation-based frameworks such as ours have begun to emerge. For example, we've got AI Hospital. It explores multi-agent interaction, but it's really only text. There's no multimodality to it whatsoever. We've also got Agent Hospital, which simulates roles such as doctors and nurses, but it's unfortunately closed source and does not incorporate any sort of medical images. And finally, we have Agent Clinic, which it goes a step further in introducing a multimodal benchmark. It's kind of the benchmark we use to evaluate our system. However, it's relatively constrained. It's just chat only, and it's not fully dynamic. So while each of these frameworks, they push the field forward, there's still a need for an open source multi-agent environment that supports richer multimodal diagnostic interactions. And that's what MedAgentSim contributes. With that gap in mind, let me show you how we designed our pipeline. So our framework has basically two main phases. The first is the conversation phase you see here on the left. Basically, the doctor agent interacts with the patient through multi-turn dialogue. The patient describes symptoms, and the doctor must decide what to ask next, whether to order a specific test or not. And very importantly, the measurement agent only provides the results when specifically asked by the doctor. When the doctor seems that all the information is collected, the conversation is sufficient, only then do we move on to the second phase, which we call the experience replay phase. Here, we have the completed conversation. It's passed through some memory buffers, which I'll discuss shortly. We do some KNN few shot on these memory buffers to extract the most relevant prior history based on previous simulations. We then supplement that into the original conversation and pass it into a group of different doctor agents. Each agent is basically fine-tuned and prompted on a different task. Each agent performs a chain of thought. They reason on their own. Once they form their own independent diagnosis, we then perform majority vote ensembling. What that basically means is the most common diagnosis between all of these doctor agents is what's picked as the final diagnosis. And that final diagnosis is passed into our record store module. So what the record store module basically does is where we present the predicted diagnosis from the pipeline to our ground truth diagnosis. If on the first pass the diagnosis is correct, we store it in our medical record buffer. However, if there's a misdiagnosis, if the diagnosis is incorrect on the first pass, we perform a reflection phase where basically we inform the doctor agent that unfortunately the diagnosis is incorrect, and they need to basically reflect, look over the symptoms again, look over the conversation again, and reflect why that diagnosis was incorrect and form a second diagnosis. If that second diagnosis is indeed correct, it is stored in the experience record buffer. Otherwise, we just discard that entire experience. And the reason we separate medical records buffer from experience record buffer is that LLMs, they greatly benefit from failure-driven fine-tuning. So now let's take a look at our results. We can see that MedAgentSim consistently outperforms the previous state-of-the-art baseline across the board. On NEGM, accuracy rises from 20% to 26.7%. On MedQA, we go from 62% to over 70%. And in Mimic IV, which is the most challenging setting performance by far, the performance jumps from 42.7% to nearly 80%. So these gains are not just marginal. They show that by forcing the model to reason and learn from past cases, we can more than double the performance in some scenarios. We also performed an ablation test where we basically looked at how each component or reasoning strategy contributes to performance. Starting with measurement requests, we see a modest gain. Adding memory replay on top of all of that produces a much larger improvement, and incorporating chain of thought reasoning raises the accuracy further. Finally, when we add ensembling on top of all of that, the previous components, we see the best results. So the key point here is that these gains, these improvements, they're cumulative. Each stage builds on the last. So, for example, when using Llama 3.3 as the backend LLM, accuracy rises from a baseline of 54.7% to 70.8% when the full pipeline is applied. So that's an overall accuracy gain of more than 16%. We've also done an ablation study on how large language models powered by our agents, how they respond to biases, both cognitive and implicit. So a cognitive bias basically refers to systematic reasoning shortcuts like confirmation bias or basically any sort of assumption about recency bias. We've also got implicit biases, which kind of reflect hidden associations such as gender, race, or even background. So in our experiments, the agents powered by models such as Mistral or Mixtral they were the most vulnerable to patient cognitive biases, while those powered by Llama and ChatGPT models, they showed greater stability. But most importantly, our key finding is that by adding our reasoning strategies, we improved these variances across the board, independent of the backend model. So, to summarize, the main challenge we set out to address in current medical AI benchmarks is that these benchmarks, they're static, right? They don't reflect the completely realistic diagnostic practice, which is multi-turn, uncertain, and test-driven. With MedAgentSim, we introduce an open, multimodal, multi-agent simulation where doctors, patients, and measurement agents, they interact in a realistic manner. So this system supports multi-turn reasoning, active test request, and self-improvement through memory and reflection. Across benchmarks like MedQA, NEGM, and MIMIC-IV, this approach basically delivers significant accuracy gains across the board and also improves robustness to biases. So in short, MedAgentSim moves beyond static question answering, bringing us closer to realistic, trustworthy, and clinically relevant medical simulations. So thank you all for your time. Our code, datasets, and simulation environment are all open source. You can find them on the QR code here. If you'd like to discuss this any further, we'll be in poster session 4, poster ID B79. Thank you.
Thank you.